we're going to solve a very, very, very common problem, and then we're going to move to the wheel. Once we go through this first common problem, you'll kind of go, oh yeah, I get this. Right, so let's first take a little bit of a navigation around the system itself. If you've already started Matlab, you'll notice up here you have Simulink. I'm going to click onto Simulink. Now, what actually happened is this became so famous that what Matlab did is thought, right, this is a real do to make some money. And what they actually did is they split it into a separate piece of software. However, Simulink cannot exist without Matlab. So in other words, if you want Simulink, you've got to buy Matlab, even if you might not want to use it. So you must use it. Then what they did is they realized so many people were using what they call toolboxes. And you're going to see the toolboxes today. I'm going to show you the toolboxes. But what they actually realized is so many people are using these toolboxes, what we could do is sell each toolbox. So they do now sell each toolbox. Each toolbox access that you'll see on here is, I think for the educational license, we actually pay, I think it's £750 per toolbox per year. Now, I'm told, I'd need to double check this, but somebody recently told me that to buy Matlab as an entirety, everything they offer in one piece, it is 198,000. So it can do a lot of things. Now, this software was famously used for the Curiosity robot. When they sent Curiosity to Mars and they wanted to predict how it would behave as it was hitting the atmosphere of Mars and how it would land, they used part Matlab and part of, I think it was Abacus, which is another FEA method. But Matlab allowed to drop all these different elements in. Now, as I said last week, what we're going to start looking at is the actual software people have been using. Well, one of the authors of the original software is called Matt, not me, and he made a wind turbine. The turbine, air hits the blades will turn, the rotor turns, that rotor then passes through to a generator, and then you can actually simulate right from wind through to power delivery. And as a demonstration piece, it's phenomenal, absolutely phenomenal. If you want to get a little bit more of an insight, there are some active examples. Now, we're not focusing on Simulink, we're actually focusing on multibody. Now, these are some great examples. I don't want to open these because it will lead to quite a bit of confusion of what the hell am I looking at. So what I want to do is just start off nice and simple, straightforward. So we're going to do a mass spring damper. We're going to look at that solution. This mass spring damper is a method of solving the notes I gave you at the end of the last session, where we had the double mass spring damper. I mean, where we had this the second order system. This is that solution. So I've clicked on a blank slate, a blank model. Excuse me. Right, so this is its entirety. This is what's praised to death. I know when you first look at it, you kind of think, this is rubbish. What the hell is it? Not intuitive, doesn't tell you much, doesn't give you an insight, doesn't say start here. It's just blank. However, don't be confused by this. If you look to the left, we've got library browser. So what I'm going to do is open the library browser. As I open this, what it will do is open all the toolboxes and everything that I presently have installed on this PC. So there will be some extra bits which you guys probably won't have. Once you've clicked on library browser, this is at present what toolboxes I have installed. These are just things for me that I wanted to use. So there is a few extra bits where you go, what the hell is that? So as a bit of an overview as to what we will be really focusing on. We will be using a lot of Simulink tools. We'll be focusing more around SimScape, but we will be using Simulink tools. So if I just look at commonly used blocks, on here we've got buses, we've got demuse. Don't mistake that, by the way. Everybody says it's a demux. It's a demu. The thing is, I had a French student who quickly put me right about and we have the gain. We're going to work on these, we're going to use these tools, we're going to use products, we're going to build equations, and we're going to drop these onto geometric representations. But what we first need to do is get a head around exactly what the hell this system does and how it works. So, I'm actually going to call up a nice image. Makes my life easier if we can actually visualize something. This is a cracking example. Let me just open this up as an image. Open. Cracking example. Okay. So, mass spring damper. Spring stiffness, C for the damping coefficient. It's fixed at a particular point. It has a mass. And our force, for our case, we're going to use gravity. We're going to let this bounce. All we need to do from this point is we need to understand how this thing moves. This is how the system works. So we know if we're hanging this downwards, if gravity is moving along the, in this case, x-axis, we know that that is the particular point. We know it moves in what we call a prismatic fashion, so it will move backwards and forwards, backwards and forwards. For this example, in reality, if it's slightly off, it might move around its axis completely. We can incorporate that, but let's not overcomplicate things just yet. So, what I then do is, that's my common problem. That's a real common problem that is brought up an awful lot. So what I'm going to do is just minimize that, and what I want to now do is take a look through multibody. So this, I've gone to SimScape, got driveline, electrical, fluids, multibody. So I'm going to extend that. Right, so on here, these are our key tools that we're going to play around with. So on this, you've got things like belts and cams. We're going to do a little bit of belts. This is a tool. If anybody's aware, simulating belts, simulating the process of a pulley system is very tricky. The process of it is very tricky. Getting a true representation. I mean, if it's moving around a curve, it's very tricky. But if it's moving linear, if it's just all pulleys in one fashion, it's dead straightforward. So it's a bit of an interesting one. Bodies and elements, we will be examining, we will be using this quite a bit. We'll be using bodies from a file because we may want to bring in geometry. We're going to be using solid geometries. We're going to use that in just a moment actually. Constraints, as you'd imagine, we can hold things in a curve, we can hold things at an angle. Curves, this allows us to dictate how something will move along a spline. One thing to remember, simulating something as simple, well, as what we say is simple, as rope or string is incredibly difficult. Because one issue that we always face is how do we represent each point of axes? How do we represent how it moves and changes? How do we clearly note how these points move as it moves? We're going to re-examine this again and again because I want you to be aware of how these things function. When it comes to forces, we've got all different elements of forces that we can use. There is different things that we're going to apply. For this, we're not going to be using any of these today. We're going to be building our own torque input. Frames, this is about where something sits, geometric representation in space, how it sits there. And when it comes to gears and couplings, with gears, where again, I'm probably going to reset another example that I had last year from an example which is a gearbox. Setting up gearboxes are very tricky, very challenging, and we are going to be doing an example of a gearbox. So it's good for your experience just to know how to do it. And then joints. This is just the relation of behaviors, how something moves in space. If it doesn't know that it's a joint, it will just consider it to be rigid and welded together, if you will, or one piece of geometry. And then finally, utilities. Now, I'm not going to explain that just now because I want to use that in just a moment. So, rather than me just explaining the block by block, what I'm going to do is we're going to start examining each component and what it is, why we're doing it. So, when it comes to a system like this, if we're going to use gravity, let's use it sensibly. So, if I say that this geometry, can I actually rotate that? I can't rotate that. Oh, that's a shame. Let's say that our gravity moves along the x component. We know that that's a fixed point there. What we need to choose is where is our starting geometric representation in space. Where are we going to start this simulation from? The obvious thing that we know is that that fixture is not going to move. So this is a great place to start. So we need a fixed point. We need a 0, 0, 0. For those of you who are CAD savvy, we need a datum. We need a starting position. So what I'm going to do is first, I'm going to drag in a mechanism configuration. Now again, I'm just going to drag the blocks in first to explain what each one does. So I'm going utilities, mechanism configuration. I'm going to go to frames and transforms. I'm going to bring in a world frame. Then I'm going to go to utilities right at the top where Simscape is. And I'm going to drag and drop, where are we? Solver configuration. Right, so I'm just going to make this bigger. Now, if you're ever in this position and you want to zoom to fit, press spacebar. So the one thing about Matlab, those of you who have been here from the start in UClan, you will know this with Matt, but I just want to show everybody so they're aware. One thing about Matlab is it has some incredible tools with it. What we're going to do is we're going to examine these a little bit more, but I do like to just introduce you to some of these things. Now let me just find, because they've moved some of the tools around this year. Right, so under modeling, under model settings, I'm going to go to model settings. We are going to re-examine this, but I just want to show you. See where we've got all these options here. We're on solver. We know that we're running for 10 seconds. Solver details. Under the details here, it's set to auto. But if I drop these are the variable time step solver configurations we can use manually if we want to set them. We've got some of the biggest names actually on this list, being Adams. We've got, well, I mean, Adams is one of the massive, or Diamond and Price. These guys really do define how well this thing works. We can set, now don't follow me on this, I'm just going to show you. If we go fixed, again, now we're actually in the position where we get our runge cutter. We have our oiler. We have our backwards oiler methods. As much as a lot of people do think that Euler's methods are dead, they're actually not. For first order and second order systems, yes, runge cutter is far superior. But when you're talking about rotations in space, Euler rotations are phenomenally good for what they need. I used it myself on PhD when studying the dynamics of the compression ring, and it gave me incredibly good results with that. So now if I go to variable time step, this is a method that's known as iterations. Now if you remember last week, we did the number of sequences within that coding, and that gave us that iterative response. Now what Matlab can actually do is actually use what's called predictor-corrector methods. Now what it will do is it will, in essence, it will rerun the simulation between, well, let's just say 8 times. It varies. And depending on the distance between two plots, if they're very similar, what it will do is it will lengthen the time step. If they're not very similar, it will shorten the time step, and it actually makes it a variable time step method. But rather than it being fixed to one solver method, it will run through all ODE methods to try and find the most adequate solution for what we're looking for. This is a phenomenally powerful bit of kit. But that is why last week I wanted to go through the scripting method, because when you went through the scripting method, we used Euler's method for the first order equation, but we actually set our iterations. This now will do some forward calculations for us, and it allows us to do that. So if I cancel that, so just make sure nothing's saved. If I go into my solver configuration, Now what we've got is how much tolerance of our error are we willing to accept. If you do go too low, this thing will crash and it just will not work. I always start off with the default and I see how we're going to work. Now, I don't suspect in anything that we're going to do in the module we'll really need to change that tolerance, but it is an option if you need to. The good thing is as well, the predictor correctors, when they run, if they notice that you've got a problem and something's going wrong, it will actually tell you this is looking a little bit odd, try changing this value. Matlab can be very nice with things like that, and again in some cases it cannot. So just keep that in mind, it can be a bit of a pain sometimes. Right, so now what I'm going to do is we've got the solver configuration. This is here so we can tap into them key solvers that we're looking at there. If you're a budding physicist and you wanted to test your own theories, which I know it sounds crazy, but I have actually had some students before who had methods. They built their own solver. It didn't work, but the initiative of trying to do it, phenomenal. So you can replace that with your own version if you wish. Now I'm just going to I'm no physicist. I am no not to this degree anyway. So what I normally do is I'll presume that these guys who've been around for a long time knew what they were talking about. Right, so we then have mechanism configuration. Now on here, as you can see, we've got uniform gravity as a constant. If you drop that, we've got time varying, we've got none. You can choose the component. You can actually make that component a variable. So when the simulation is running, you can actually have gravity changing. Why is that useful? Because if you're coming from space through to the stratosphere, through to a planet, you can actually incorporate the changes in gravity as it's actually entering it. You can incorporate all sorts to it, but it allows you to do that. Also, if you wanted gravity to move for some God knows reason, you can also do that. But for us, it's incredibly important to know where gravity is sitting, because we're probably going to have to configure this to suit. So I'm going to click OK. And then finally, our world frame. What this does is it gives us our starting point. It tells the system, I am starting here. It tells us this is my datum. So then what I'm going to do is come back and I'm going to place this into position. Now, if it's the wrong way around, press Control, keep your finger on Control, press R, R, rotate it round. And what I'm going to do is just bring this down here, press Control, R, 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 because these three need to talk to each other. Left click, drag, connect. Left click, drag, and connect. Like that. So this now is our, let's say we've just set up gravity, we've set up where we're starting from, and we've told the system we're going to use the system solver configurations. Okay, so let's move this on a little bit. Now, what we know, hang on a second, let me bring that back. What we know about this system is that it moves this way. It goes backwards and forwards. When you're working with something like Matlab, like this, it needs to know the dynamics and how them dynamics are attached to the target. And in our case, the mass. So first things first, we need to tell the system how our geometry is going to move. So I'm going to go down to joints. In them joints, what I can do is drag and drop a prismatic. We have all different types of joints here, but the prismatic is our key one. So I'm going to drag and drop it in. And I'm going to spin that round. Whoops, wrong button. And then I'm going to connect that up. And all that does is it literally says to the system, this is what I'm doing. This is how I move. I move backwards and forwards along the Z axis. The one thing I've not told you yet, every single axis in this system is presumed to be Z. If it's in the wrong axis, we need to change it. We need to move it. In a moment, as I said, we're going to solve this, get this running, and then we're going to move on to the actual example that I wanted to do, which is the wheels. We're going to look at the wheels, and we're going to look at incorporating the wheels into the system and getting a solution based on the actual notes. I don't know who's actually seen these notes. These are the notes. These are on Blackboard as we speak. This was solved in SolidWorks, and I think I actually gave a... Did I give a Matlab example? I did give a Matlab example. Oh, it's the old school one. I've just realised. Oh, that's not good. It's okay. We're gonna do an updated version. I need to update that. I've only just realised that. That's awkward. Right. So we've got that motion now. Now the other thing that's quite interesting about this is that it has an assembly on it. It has the mass. It has a spring and the damper. So what we're going to do is we're going to bring in a spring and a damper. Now under force and torque, you'll notice that we've got spring damper force. I just realised I changed that position. That's really odd. Anyway, you'll notice that we've got spring damper force. Because what this will do is this will solve the spring and the damper configuration element to this. So I'm going to drag and drop that in. Now I'm just going to stretch this out just a little bit, just to give it a bit more space to be freely move around. Now the way that this works is we need to say where the base of this is and where the follower is. Now think of it like this. You can either call it back and front if you wish, but it is base where it's connected and the follower of the geometry or whatever it is attached to, which, well, it needs to be geometry. So I'm going to spin that round for a second. Spin that round. So again, this base is my grounding of where the spring is. So now what we've actually built is we've told it where gravity is. We've told it where it's fixed. We've told it how it will move. We've told it where the spring and the damper actually are. We still don't have geometry on there. There's still a little bit more to do yet, but we're getting that one step closer. So first things first, I'm just going to have a quick navigation through these tools, make sure I'm moving in the right direction. So I've not introduced these yet, so if I go to joint, I'm going to double click into joint, and we've now got the prismatic joint. This is everything. This is amazing, by the way. But this is everything we can extract from this joint. So we can extract constraint forces, total forces, torques. That's coming from the joint itself. So this could be forces around the spring and the damper. The model configuration, with that, we can actually really change a lot of its inputs. We can sense different positions, how it's moving, how this joint's moving in space. Actuation, we can force this thing to move. We can tell it to move how we want it to. Notice that it's only coming under force because it's prismatic. It is almost control of a non-affected vector, in lack of better words. Limits, we can say how far this thing is allowed to go and what type of operational workspace it actually has. Initial mechanics, we can set this thing already moving. Now the beauty is with this is you'll notice that there's a spring and a damper coefficient in there. Now not a lot of people know this, but the springs themselves, the material that's in them, actually have a natural damping and a natural spring stiffness to it. So it's what you can do is you can drop in further refinement to the behaviour of that spring just on the material itself. So that then will be combined with the spring force response. And then finally, your state targets. We can set a position, how something should sit, where it starts from, and velocities. We can even say how something's going to move at speeds. So we initially hit it with a key velocity. We're not going to use them today because I want to actually build in some elements to it. Now let's jump over to the spring and the damper. Spring and the damper, as you can imagine, we've got a natural length of it, we've got a spring stiffness, we've got a damping coefficient, as you'd imagine, and we can sense force coming directly from there. So these two will do very similar jobs, but because it's a spring and a damper, I need to tell the system how it's going to behave. So, next thing, we need now to drop on the mass. So we're going to set the size of a mass and then we're going to drop it in there. So I'm going to go back to the simulant library. I'm going to scroll down and then I'm going to go to bodies. These bodies now I can choose all sorts. Now I can just use a brick. So I'm just going to use a brick solid. So I'm going to drag and drop a brick solid. When it comes in as a brick solid, it's as you would imagine. It literally says, that's my dimensions, how big do you want me to be? Happy days, let's do that, whatever. What I'm going to do is, I'm probably going to do it half of all that. So these are dimensions. Now, these are your typical dimensions in any CAD, any sim systems. Any binary methods, anything like that. So this is simply X, Y, and Z. So what I'm going to do is go 50, whoops, 50, and 50. I'm not going meters. I'm going to drop my meters, and I'm going to go to millimeters. I'm going to press F5 to update. Now this is a bit more like what I'm actually after. So we can play around with densities. So if I just bring it up here, stretch this down a little bit more. So I can play with inertias for my density. So within it, I can set it by density. I can set it by a point mass. I can set it by custom. Now with custom, I can actually put things in systematically to make sure that that mass is truly represented and correctly represented. If I don't want to set it by density, I can set it by the mass itself. I mean, 1 kilo for a start is not so bad. It's a good move forwards. Now, I think we have a question coming through. 2 seconds. Nope, we do not. Just like to be sure, that's all. Now, once I get here, derived values. If I just say update, what it then does is it takes it, it will take the density, it will take what I've put in there as a mass, take that density, give me a centre of mass, give me a moments with it, it will give me the products of it, which obviously in this case is not much. What I'll perhaps do though for this example is I'll set it back to its normal, click an update, and that. So I'm on density, I'm on 1000, I think that's, correct. Somebody correct me if I'm wrong, I think that's water. 1,000, I think. I need to double check, but it's not much, or maybe even air. From here we've got graphics. As we move through, I know it sounds crazy, and as we move through, you're going to need to recolor. Now this is a simple part. The next 2 wheels are simple parts. These are single parts, but we are going to move to assemblies. Assemblies get very, very, very confusing, so it's often easier to colour your part. So if you colour a single part, when assemblies come together, you can clearly see these parts working like they need to. I did this personally when I was doing piston rings, because when the engine was running, you could genuinely see this big red thing moving as it should do. And frames, we're not going to examine frames yet. We will be doing, but added frames are something that we will be touching, but not today. Right, so we've now got our brick in position. We've got a size for this brick. It's 50 by 50 by 50. So now what I want to do is I'm going to come up here, I'm going to spin this round, and I'm going to attach it. Now, as it's attached, what I also want to do is bridge my spring and damper across as well. So what happens now is the spring and damper knows where it's going to be, and the prismatic joint knows where it's going to be. Now if I could just come back to my model, so at the minute we've actually got everything in position and everything should be running, or at least that's what we're hoping. yeah, at least that's what we've not set. I've just thought we've not set a spring stiffness yet. So let's set a spring stiffness. So let's go. Let's go. Oh, yeah. Well, I'm just making this one up off my mind. Actually, I'll go 50 Newton meters for the spring stiffness, and I'll probably just go 50 Newton meters per second for the damping coefficient. So it's almost balanced completely. It's almost balanced completely. If I click apply, then okay. And what I'm now going to do is, if you haven't already, hit save. So, because the trouble is now we're getting into a really good spot where this can go either really right or really, really wrong. So I'm going to go desktop, and I'm going to go mass. Don't forget with Matlab, no spaces. God, it irritates me. Mass spring damper. So I'm going to save that. Oh, current save because the model of the same name is open. Okay, then I'm going to go mass underscore save. Ooh, there we go. Right. I've had a question here, or more of a statement here, which I do want to read out because it's a very good point. I'm aware of that this might have happened, hence why I wanted to do a video. So I've had a question saying, I've downloaded Matlab 2020 from the University Guide. However, I have an option. I don't have the option multi-body and a few of the others which you're using within the lecture when I go into Simulink. Okay, so you're absolutely right. I was aware that this might come up, so this is why I'm going to do a video. You've got a great point, 100% great point. I'm going to take you through what we're using. I'm going to make sure that everybody has it, because it dawned on me. We've got all these 20 million toolboxes, but you guys may open it and just go, the hell. So again, I'm going to make a short video. I'll probably produce it today. It's only going to be 5 minutes. And it's just showing you the boxes that I've used and that I'm using on here. So I can't solve it now, but I will solve that today. That's the best answer I can give. I suspect you're not the only one, so good question. Right, so we're actually on here. I'm going to I still, as much as it doesn't solve that problem for you, I'm still going to solve this just because I want people to be able to chase that back up. So let's get back into it. Happy days, kind of. I've got questions coming left, right, and centre here. Oh, something else. Right. So if you've not done already, make sure you save it. We're now in a position to hit run. So I'm going to hit run. Hang on a second. There we go. So I've hit run. It's compiling it. It's bringing it together. I'm really excited. It's all going to work. Is it going to work? Please work. So. Oh, what? But I. Oh, that's depressing. So, that didn't work. I'm just messing with you. I genuinely know why this didn't work. We've not incorporated one important thing. This just gave me a good opportunity to show you not how great it is when it all works, but what happens when it goes wrong. Now, the one thing that still irritates me with Matlab, if I run that again, I just want to show you the output. Error evaluated, equations at time 00, stopping simulation. This may be singularity in the solution. If not, try to reduce the steps, and you go, okay, not sure what that means. It's crazy. It is crazy. You can look and go, that is not telling me anything. We're going to work our way through what that is. And when you look and you kind of see what Matlab was trying to tell you, you go, okay, yeah, it's still not clear, but okay, yeah. Now, this is the visualizer. These visualizers I find incredibly good. They're really good. Once you set up the simulation, you can see this thing. It gives you an idea of where everything is. Every axis sits in Z. So let's take a look through this. Mass spring damper. So let's go on the mass spring damper. We've got on the mass spring. Oh, hang on a sec. Everything is in Z. Let's compare this against our original set. So if we go over here, you look, and we actually said that the spring and damper would be connected at the top. But the spring and the damper is connected in the middle. So this is a geometric, well, it's just wrong. I'm trying to think of a very sexy term. It is just wrong. Now if I go to prismatic, don't forget, all that is describing a behaviour. So as long as our mass is going to move in that z-axis, it's going to be good. It will move in that z-axis. Brick, well, brick's a brick. You know, it just tells us the size of that brick. So if I go to world frame is where that grounding point was. If I go back to world frame, you realise it's sitting in the middle of the brick. You go, damn, wrong spot, entirely wrong spot. So what we now need to do is to move that brick. We need to move it into the correct position, so that in essence this then sits at the top, and it's a true representation. So I'm going to close that, because we now need to figure out how to actually move it like we want to. Now, so what I need to do is go back to the library. So I go back to, I've got so much stuff open here, hang on a second, let me just close some of this junk. Yeah, so I'm going to go back to the library, and what I'm now going to do is I'm going to transform it. And when you're talking about geometric representation and you're going to transform along a particular component, all it means is move it along that Z, X, Y, J, I positional state. That's all you're actually saying. It's nothing, you know, it's nothing over the top. So if you look here, we've got a reference frame. We're going to examine this, not today, but we are. And you have a rigid transform and you have a transform sensor. Rigid transform is phenomenal for what we need to do. So I'm going to drag that in. I'm going to bring that across. Again, all it does is moves along an axis. Nothing more. That is it. So, we got this transitional state here. We know that it's actually not about the behaviour. We don't need to move the brick around the behaviour. If I drop the spring, in fact, don't follow me on this, I'm going to show you what happens. I'm just gonna comment that out. So what it does, it makes it vanish. And if I run this again, watch this. There you go. And all this does now, this drops into oblivion. This is purely because the system knows that gravity moves in that Z component. So this is great. Now, the thing that's breaking it is the incorporation of the spring. So we know that if it works like that, it means all we need to do is we need to move everything relative to these two. So what I'm going to do is move this around. I'm going to just, now I like, this didn't always work by the way, but if I just move it in, it snaps itself in automatically. I love that. The base to the follower, so I'm saying at the base, at the ground, I want to move it a certain distance. So I'm going to just double click in to take you on a little bit of a navigation around how this thing actually works. So we can choose to rotate it. Rotation, if you've got very complex geometry, or if you've got a real idiot who's drawn something completely wrong, this proves to be problematic. This can prove to be a problem. What you can actually do though is you can rotate things and you can move things around. Translation. You can use Cartesian, which is the XYZ component. You can use standard axis. Now we know which way we're going to go with this. We know how we need to move this, and we know where it's going to move. We're actually going to move along that Z axis in the negative method. Make sure you change your units, by the way, to millimeters. If you remember, we did 50 by 50 by 50. We're coming from the center, so as ever, 50 over 2 will go 25 millimeters. Click apply, and all that will do is shift it 25 millimeters. So let's run it again. Let's take a, whoa, ho, 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 ho. That is more like what we were looking for, ladies and gents. We were looking for more of a much better approach. And the thing is yes, okay, so if I run it, we kind of go, yeah, okay, so what is that really telling me? It's critically damped. It's not responding as we want it to. But let's, rather than just seeing that simulation, let's start to pull some results out. What are we actually looking at? So, in the notes that I gave you last week, for those of you who actually did go through it, you'll know that you could plot position and velocity. So what we're going to do is we're going to plot position and velocity. Now I'm going to do it based on the joint because it will register how much motion has occurred around it. So I'm going to go sensing, I'm going to go position and velocity. Click apply and then OK. There is some real things that you are going to have to get used to digesting. It's a little bit brutal. So you have a system called the power stream method. Now the power stream method, what it actually does is it takes matrices, so think of that Cartesian value in X, Y and Z, and it places this into a three-dimensional space. What we're asking for here is actually non-power stream, so non-matrices. We're looking to convert them linear values to something to measure. So what we're going to do is we need to convert it from power stream to Simulink. So I'll show you how this is done. Again, back into the library, we go to utilities, and you'll see PS, used to be full name, but it's a PS to Simulink converter. This is power stream to Simulink converter. We can also go the other way. So I'm going to drag and drop power stream to Simulink converter. And if we need two, so if you come across this, right click and drag your mouse down. And that is a quick way of copy and pasting. So I'm going to spin that round. Just as an intro, we are taking this dead straightforward. I don't want to overcomplicate things just yet because this software is notorious for being very complicated, as you can imagine. So what this then does, if I double click into here, whoops, come on you swine, there you go. We've got an output signal inherent. If you know what your units are, put your units in and it will give you an accurate unit representation. If you have an expression for the units, you can also do that. We're just going to extract this at the moment just to take a look at what it's given us and look at the way it's behaving. So what I'm doing now, going back up to Simulink. For those of you who know about Matlab, you can just type this and it will appear. I'll show everybody else in a second. So what I'm going to do is go to the top and go to commonly used blocks, and I'm going to drag and drop a scope. Any minute now. There we go. So from the scope, for anybody who was wondering what I meant by that, if I click anywhere on the screen and type scope, it'll also bring it in that way. So it's a useful tool to know, is that. Right, we need to configure this scope to give us something that we know what we're looking at. So I'm going to double click in and I'm going to go to the gear here. Now this gear simply allows me to configure the scope itself. So I'm going to bring in two elements to this scope. Now it says you've got two elements there, but you've not got two inputs. So you'll see there where we've got number of inputs. I'm going to go 2. Click apply. So, and now what we can do to bring this in nice is, now I do always insist that your lines are as tidy as possible. Mine could be better. This is not really acceptable, so it needs to be well presented. Presentation in this is everything. 2 seconds. Oh, another random question. Not now. So I'm going to run it again. Now as we run it again, it's not going to do anything. Well, I mean technically it is going to do something. It's going to give us what we just had. So if we then, I'm just going to bring that back. You'll notice we're running still for that 10 seconds. Run it again. That's just me, oh, that's not me just playing, that's just me running it over again. So let's then double click into the scope. So that is genuinely what we're getting. You can see there that the positional state where it moves in meters is, what's that, just under 50 millimeters? 500, yeah, 50 millimeters it moves. And then you look, you'd think of the size of how big this is, fair enough. Now you look at the velocity of this, it starts off not much at all. I mean, its maximum that it gets to is 0.5 meters per 0.005 meters per second. It's not moving quick at all. However, what if we wanted to then look at introducing this as a bit more of a dynamic system? So let's go back onto here. What I'm going to say is, right, oops, I don't want that. What I'm going to say is, right, let's drop that and go to, let's just increment drop that and go 45. Then we run it again. We're still very much, so if I then look at the actual sim and run it, still heavily damped. Okay then, let's go 5 and 2. This might give us a bit more of a dramatic response. Still not much in there at all. So I'm going to build up my spring. When we build up a spring, and let's face it, when this sim runs, when the simulation runs, you can see there we've got this initial response for position. It'll return itself at its steady state for its position. This is absolute, by the way. And then what it will do is it will continuously resonate around. So what I'm going to perhaps do is just drop this down to a second, and then I can run that again. So on the sim now, if I just simply go to stop time of a second, and then if I run that again, what we're now starting to get is the way the positional state's moving. We can change this if we wish. We can check out the body if we wish. We can do a lot more to this, and what I might do is, as we're going through, revisit this and do some more nasty stuff to it and just do all types of different things to it to see what type of effect we can get from it. But that is the basics. That is the dead basics of how we move into these states. Often if it's a bit too messy, which this is starting to look a bit messy for me, what I like to do is create subsystems. So I left click, drag a box over, I'm going to right click on there, and then I'm going to create a subsection. So if I then bring this down and then spin it up. Oh, I think that looks even worse. Oh, that is not good. Oh, that was not good at all. So I'm going to go there, there, and there. Okay, let me go there, there, that, and that. Let's try that as a subsection. Oh, that is nasty. Don't like that at all. Yeah, when it comes to this assignment, I am very difficult. Just because it needs to be very well presented. That's irritating. I'm going to sort that out. But anyway, that's a side note of what we're doing. So what we can actually do now is, if any of you have already realised this, you can actually now turn this into variable states. Just want to do one more thing to this, and then we're going to move on to the wheel, because that is more of an example of where we're going to go with this. And M is equal to now what we'll do is we'll go M is equal to 50. We'll go C is equal to 50, and we'll go K is equal to 50. in here now, what I can do is go onto here and then go M, M, and M. The mass, I can go to here, do the same thing, M over 2, then come to here, then go K, and C. This seems dead simple for something like this. Seems a little bit over the top for something like this. However, if you're doing a gearbox, if you're doing a variable piston, if you're doing a variable conrod or crank ratios, it can be a nightmare changing everything over one by one. Often the best way of doing it is controlling these through variable. So if I run this, I've now got even more control by simply typing in, I could just say M is equal to 100. Now what the system will do is, because that variable's changed, when I run it, it might go a bit wrong here because I've just randomly chosen a value. When I run it, now the mass is a lot bigger, and when it runs, we're now back in this state again. And don't forget, I set it by the density of it, so the bigger it gets, a greater density is going to emerge. Right, so if you've not done already, make sure you save that. That's the basic intro to using this system. So I'm going to close that, and I'll save that. So the other thing that this system can do is it can read from geometry. What we're going to do is we're going to look at, let me just, oh my Alexa's going off like mad. We're going to look at these two wheels. These two, I've already given to you. If you look on Blackboard, you'll see wheel models. Both wheel models are there. They're already in step format, ready to go. Right, so what we're going to do first is, let's start a new model. So I'm going to go to new model. And what I like to do with something like this is I like to set up the environment. So I'm just going to go here, and I'm going to call this a torque sim. I don't know, have I got these downloaded? Let me just have a quick look. I don't have these downloaded. They may be on Teams, so 2 seconds. I'm going to jump onto Teams. I hope I put these on Teams. I better bloody had have done. If I've not, they are on Blackboard. Just a nice test for me to just double check that they are there. And brilliant, no I didn't. Right, so on Blackboard, so let's go through to Blackboard and let's go and get them. So on here you'll see wheel models. So I'm going to left click. It will download a zip file. In the zip file you'll see wheel 1 and you see wheel 1. You will see wheel 1 and you will see wheel 2. So that is how the zip will look. I'm going to highlight them both and I'm going to drop these into my simulation block there. Right. Let's take a look at setting this up. Double click in, everything's there. Let's start a blank model. My blank model, this is the same as ever. Now think about this. This is a wheel spinning around a particular axis. What do we know about gravity? Same as before. What we're going to do is set up the same as before. Set our grounding up. So I'm going to drag and drop. Mechanism configuration. I'm going to move much quicker on this now just because we've already covered why I'm doing this. I'm going to drag and drop a solver configuration. I'm going to drag and drop a world frame configuration. I'm going to bring that in, spacebar. Now I'm going to spin it round to have my three-way configuration like this. Again, if you prefer to have it slightly differently, you're more than welcome to it. I'm going to pause for a second for the wheel because it's key about this. Now with gravity at the moment, we don't know how the wheel's coming in. Let's pretend for 2 seconds that what we're actually looking at is a somebody's piece of work and we don't know how it's been modelled. They've either done it right or they've done it wrong. We need to choose what is the best way forwards. So I'm going to click OK with that. And right, so we're thinking about a wheel moving around an axis. Let me just call these notes back up. It's a great way to look at it. So if we look at this wheel, we know the axis sits along here. So if it's moving around that axis, we know it's going to be some type of revolving thing. Now don't forget with this system, always needs to know how this thing's going to relate, how it's going to move like we want it to. So what I'm going to do is bring this out, bring this up. I'm going to go down to joints. Where are we? Joints, 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 joints. Joints, whoops, joints. And we're going to go revolute joint. Drag and drop my revolute joint. And I'm going to spin that round like that. Bring that in. Right, so on here at the minute, we're not changing anything because we don't know what we're starting with. We don't know for sure what's going to happen. Next thing that we know is we're going to bring in the wheel. So I'm going to drag and drop a wheel in a second. Where are we? We're going to go body. Through these body options, we've got file from solid. Drag and drop. Excuse me, I cannot stop burping this morning. I'm going to bring this up and tag it together. On here, I just want to call this wheel 1. I'm going to double click in. Now, this system uses what's called address pathing. We are going to examine this a bit more. For this, I don't want to complicate things for this, so I'm just going to automatically do it. So under file name, you see the 3 dots. I'm going to click on the 3 dots. It's now asking for a path. Where the hell is your model? So if I go torque, and I'm going to go wheel 1. This system prefers to read from step files. Step files are, there's been lots of translational arguments for years. What is the best way forwards? IGIS was on top, then funnily enough STL, stereolithography files, were on top, and then step files. And step had one particular point, and the new one, 214 step files can actually record lots of extra data in it as well. So there's an awful lot of stuff going on in that. So what this will read is step files. And click open. Now you see there, parameters variables, so press F5. And then I'm going to use my zoom to fit, and there is our wheel. Now, what's the most important thing I need to know is, where is that bloody datum? So if you look on the datum, the good thing is whoever drew it correctly. You can find sometimes that if that hole is on the y-axis, you've got to spin it. Granted, I did draw it like this to make this particular set of notes easy to start with, because I will be giving you ones where the geometry is all over the place. Then what I need to know is, where is the axes attached to this? So if you look here, I've got toggle frames on. So if I click frame on, we look here, and it means it's actually sitting there. So in other words, great news, we don't need to move anything. We've actually got everything in position like we want it to. Now based on the notes, what we do need to do though, is we need to add a geometry, where we need to add a mass to this. Now I'm going to operate directly to the notes, so I'm going to go inertia. I'm going to go calculate from custom mass. Now it's literally saying, well, how big is your custom mass? Now don't forget, I already know what these geometries are from the notes. I solved this originally in SolidWorks, so I knew what the geometries were from the notes already. I'm only adding this because I know what it is. So I go 65.87. Now this is purely because, as I said, I already know, and if I know what the material is, it doesn't matter the mass as long as that mass is correct. So you can put in that custom, or you can go density, whichever way you want to go. So I'm going to go update from that. So everything now is updated. I'm going to press F5. If you want to colour it, you're welcome to colour it. I'm not colouring mine in, which sounds odd to say, but you know what I mean. So I'm going to click apply and OK. So, as I said before, we are getting to a position now. It's going to get a little bit hazy, so I'm going to go save as. I'm going to navigate to my torque sim, and I'm just going to call this sim wheels. Click save. So I'm now set up and now ready to roll. Because it's wheels. And then I'm going to hit run. Obviously nothing's happened because I've not applied anything to it. I've not said how this thing's going to start moving. I've toggled this axis on because if it starts to move or something affects it, I will know about it. The other thing is look at where Z and X are and look at where Y is. Really, if this was on a, let's say a car, again I know it's just a very odd shape, but let's say it was used that type of axis, we know that gravity would be in Y. I think we should move it to Y. So I'm going to close that. I can't believe how many people are requesting permission. It's not happening. Right, so what I'm now going to do is bring in, I'm now going to change my gravity. So if I go into mechanism configuration, know it's in the Z, I'm going to move my X component, I'm going to move my Z component, sorry, and my Y component, and just swap them around. So now gravity sits in Y correctly. And even if we run it, we may see slight changes in the wheel because just gravity is affecting it, and that's it. But that's not really what we're looking for. We want to now be able to apply some torque to it. So if we go back to the notes, I'll show you what I mean. Oh, goodness. If we go back to the notes, and just go down, just go down, just go down. We're going to apply a torque to it. So let's apply that torque, and then let's get to that running. So we're looking at watts. 1.356 Newton meters. Excuse me. So I'm going to double click into that Revolute joint and I'm going to go actuation. We're now in a position where the motion is automatically computed and we've also got torque. So I'm going to drop torque and I'm going to say provided by input. Click apply and then what we get is an extra block now. What we need to do is transverse our linearized value of 1.356 to the power stream. So this then becomes a Simulink to power stream converter. So I go back to utilities and I go Simulink to power stream conversion. And I'm going to spin that round, bring that across and tap that in. Thing is, we haven't set the units yet, so let's double click in. Signal output. Okay. So from the signal output, we know that we're going to be actually applying Newton meters. From the input on here, what we're actually, the input types, now what we can do with this is crazy what you can do with it. If you have an electric motor, most electric motors will operate similar to a second order behaviour. If you have particular mass, if you have a motor which is more of a first order behaviour, you can actually tell the system, I want it to be a first order or a second order behaviour. What we are doing is we're saying, no, we're just going to make it precise. This is the value that we're feeding in, and it's going to be based on here. So if I click apply and then go OK. So again, we will be doing lots more of these conversions, but this is just to get a good feel for what we're meant to be doing. Right, so let's go what do I need? Oh yes, I'm going to go commonly used blocks, and I'm just going to add a constant. This value is just going to be introduced at that particular rate, and then we can check what type of value that we are getting. So I'm going to double click in. As you can imagine, it's just adding a value. So I'm going to go 1.356 for my Newton meters, and I'm going to apply it. Then what I'm going to do is I'm going to spin it round. Now the important thing to remember, this isn't a unit. This is almost unitless. Our units are controlled in our conversion tool. So if I tab that in, it means whatever unit I feed into that, it will be converted to the correct value that I want it to be. Again, hit save. And what I'm going to do is run that for 8 seconds. Just to make it similar. And I'm going to run it. If we take a look at conversion, you see the axis spinning? So if I run that again, you can see, if you've tabbed on your toggle view, you can see the axis rotating. So now that confirms we're doing the right thing. It's running like it should be doing. Excuse me. So, based on that, okay, so let's just come back on these notes again. I do like to stay close with these notes because it's something for you to reference to. So what we know is we have an acceleration and we have a velocity based on these particular value sets. So let's see if we can match roughly against these to see what is going on. This one last year for some reason went belly up. But we're going to see why that's happening, if that's happening. Hopefully not, touch wood. Right. So what I'm going to do is bring out on here, I'm going to go my sensing, and I'm going to have velocity and acceleration. Click apply, and okay. Bring that across, drag that up a little bit, and then what I'll do is go to my conversions again. So what I'm going to do now is I'm going to go power string to Simulink converter. This allows me then to bring out them key linearized values that I've been after. Tab that to there, and tab that to there. Now the first one should be in degrees per second, if I remember rightly. I always get these two mixed up. So in degrees per second. See, sometimes you won't even find the value that you're after. You can't look and go, well, that's just great, isn't it? So I'm going to go deg / per second. Go apply. And then I'm going to come to the lower one. Now, I'm sure on the lower one, let me just think, it was deg second squared. Like that. So again, that's on output for the first of my velocities and accelerations for degrees per second, and degrees per second being squared. Now, finally, I want to scope. So I'm going to go scope. And like before, I don't need this for now. I'm just going to maximize that. Like before, spacebar that in. Like before, what I'm going to do is double click in. I need 2 inputs. Whoops, wrong button. So I'm going to go, not that. So I'm going to go 2 inputs. And then I'm going to add in my output, my actual inputs. So we've now got 2. And just because I'm so anal with this, I'm just going to add them in like that, just to make it nice and neat. I know I'm not the only person out there, just because you get these boxes that try to help you align it. So yeah, it becomes very obsessive when you get into this. So let's run it again. So we know that the sim is running, we're getting that rotation that's occurring. Let's start looking at the results that we're getting. Is it something like we should be expecting? Oh, hell. Now this is similar to what we were getting before. We know that the output on that acceleration is fine, but this one was something that I was finding before actually. Let me just double check that I've just set everything correctly there. Uh, 2 minutes. Let me just check on. What I'm going to do is drop my accuracies, so I'm going to make it more accurate. First things first, on here you can see the relative tolerance you'll accept. I'm going to drop that. I'm going to make that to the power of 6. We'll double it up and it will make it less cumbersome and clumsy when it runs. So if I just go back again and hit run, see how it becomes more smooth, and with that smoothness it does give you more of the smooth response. This is noise that's occurring, and I am missing one particular thing from this. Let me just double check. Because that would tell me that there is something wrong with my representation of my inertias. Sets graphics. Try an update on that. Just try that again. Click F5. Let me just try rerunning that. That might be, I may have forgotten to update. Let me just go back to simulation and then let's run that again. See if that does. No, I'm still missing something there. Seconds. That has bugged me. I'm just going to drop these to inherent and see if it's having a problem with converting. Don't think it should. No, it's still not. Let me take a look at that. That seems incredibly out in comparison. That should not be giving me that. I'm just going to take that out because there's one thing I just remembered. In the original set of results that I did, what I actually did is I set all my, I actually turned gravity off to look at these raw results, and it makes me wonder if just because of that, then I could just look at the torque that was being delivered in. So based on them results that I'm getting, let's have a look. 12. Yes, this was purely because I forgot to turn gravity off, and you can see there that we're still. I need to turn them back to the correct values actually. Degrees. Oh, I forgot mine. So I always forget these blooming units. Always. I'm just looking at the notes to remind myself. So we bring that on, click apply, and then we run again. Again, I've done that. That's better. That's much better. Right. Thank goodness. This was purely because I ran it outside of the gravity. So this actually doesn't have gravity applied within it, and it's just looking at the effects of it. What we can do is we can look at the impact that gravity has when we look to change things. And that's what that's genuinely what we're doing. So we can see there it matches against the initial simulations, and we're getting actually the correct value. Now, the other thing about this is if you want to label what's coming out, and you cannot be bothered with labeling the actual plots themselves, what I'll say is angular. Get this right. Angular law. Acceleration. So accel. Wait a minute, am I on the right one? No, that's angular acceleration. That is velocity. Apologies. So this is velocity, vel. And then I'm going to copy that. So I am that lazy. And I'm just going to come back onto here and go ACC. So then if I run it again, then come back, what we've now got is labels attached to them plots. We know that the units are correct because we've put in the units into it. You still would not put that in a final assignment. We are going to go through waste of output and to do really decent plots, because that in itself is a bit poor and we need a bit better of something to operate to. So that's not what we would put in an assignment or anything like that. Let me just close that because that's having a meltdown going, why have you left me open? Right, so now again, as I said before, I do like to try and stay relatively close to these nodes, just because it helps, and it helps the initial process with it. So again, I've dropped gravity just for the moment. We will revisit that, we will add that in to look at the effects. So I mean, in fact, if we do actually drop it in and look at the effects, so if I then just bring that out and then come back to here, I'm going to comment that one out and then turn that back on, uncomment, we add that in, and then we run it again, come back in, and this is the effects of gravity. But you notice that the effects of gravity actually on the acceleration, the angular acceleration, is minimal. It's noise, if you will. But when it comes to the velocity, obviously it builds up because we have a value which is constantly being fed in. But this, as the acceleration goes, this is just the effects of gravity and the noise against it. Now this is where you do start to get differences. So if you look here, SolidWorks itself was trying to pick up on relatives of noise as it emerges. But what we can say with that, as horrible as that looks, we can say that the effects of gravity in this case are negligible. Because you look at the differences that it's occurring, it is practically, it's very, very small amounts of changes that it's actually having an effect. So we know that about the wheel. Now what we can do before we move on to anything else and move to any other conclusions, we can now bring in the second wheel. So I'm going to right click, drag and drop across, and you'll have to bear with me on this. So we're going wheel 2, and I'm going to go to from file, I'm going to now navigate to wheel 2 and then click apply. Now if you remember this one, I don't know if you know, probably don't, I'm not sure, but on this one the wheel actually now has a difference of inertia within it. So I'm going to go F5, and then on my inertia now what we've got is a custom density of, well, it's actually 7700 kilograms. So this thing is a lot bigger, a lot more weightier. So if I click apply and close, now what I'll do, right click, I'm going to comment that one out, and I just want to look at the effects. I now want to look at the effects of wheel 2 in the exact same conditions. So I'm then going to run it. If we look at wheel 2, now what we're seeing is a very, very, very difficulty in motion. So if we look at the wheel as it moves, so I've got so many windows open here, I've got myself confused. Where are we? Oh, there we are. So if we look at the wheel as it moves, we bring that in, bring on that datum and run it again. You can see its abilities, very, very slow amounts of its ability to being able to move. So the momentum of build on that is massive. So if I then go back and look at, because this was with gravity, but then if I go back and then I comment this out and then look at this without gravity, we start to get that initial mode, but there's still that momentum. It still needs a lot more to move. You see there that it gets up particular speed, but it still needs that initial... Can I actually zoom that? Let's see if I can do an automatic zoom. Oh, that's just pants. So I'm just going to see if I can zoom this axis here. But the linearization with this now is simple. There's no gravity, so it gets to its maximum acceleration and cannot change past there. I know it's not a true representation, but it's interesting to see the effects of acceleration with and without gravity. Right, so let's get back to the actual point. So I'm going to now flip back to wheel 1, so I'm going to uncomment that. I'm going to comment that out. I'm going to switch this, I need to mark that out actually. So on 0 gravity. And now what we're going to look at is what happens if we apply a variable state. So this, feeding in from a signal. Now on things like SolidWorks, it is very, very tricky to get this bloody working right. I know, because I've been there, done it millions of times. So what we're going to do is we're going to use Matlab's superior ways of doing it. I am a big Matlab fan, you may have noticed. So what we're going to do is, we are going to do that, yes. What we're going to do is, I'm going to bring this back, and I'm going to delete that, but I'm going to hide that, or comment that out. The only reason is I think it's good to keep that there as a reference. And if I go through the library, I always manually go through the library. If anybody wants to type it, it is Signal Builder. I go this way so everybody's aware of where everything is. So in is it Syncs? I'm sure it's, or Sources, apologies. In Sources, you'll find Signal Builder. Don't forget, in our last set that we'd added to it, it was just a value that we were feeding. What we can now do is be very slick. What we can now do is we can put that in, add that into there, and we can make a signal operate under our 8 seconds. So you look there, that's too long. So what I want to do is I want to change that. So I'm just going to go to time region, and I'm going to change that to 8 seconds, just so it matches, or else we're going to get very confused. I want to match exactly to the notes. So from 0 to 2 seconds. So this, come here, swine. This should be 2. So yes, 2, and it's gonna be, oh, no, that's me going wrong. So that should be 2. Sorry, it's time 2, and that should be there. So the first one that we're aiming for is, I'll just go down to the manual note set that I did for Matlab. So where is it? 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 We'll get it. Swine. I know it's here. Ah, there it is. Right. So that is what we're now going to set. So we've got the first point, we're going to go 0, 0. So first point, we're at 0, 0. When we're at 2, this now becomes 0.1123. When we get to 4, so at time we're going to 4, and at y we're going to 0.1123. Then what we're doing is when we get to 4 again, we're going to set this back to 4. So we're going to go back to 4. I'm going to set that to 0. And that gives us our initial time setup. So we're now looking pretty good. We're now looking in a good state. Right, so let's, if you've not done that, again, that is how it will end up looking. So I'm going to close that. So we're now going to close that, and we're going to study this into 2 states. So first, let's take a look at it under no gravity. So I'm going to run it. This is going to be very black and white. So if I run it, we get a strict increase on the acceleration. We get that initial momentum for the rise up to velocity. Then we're getting up to speed. We're going to get to the maximum velocity. Then acceleration drops because we set that particular point to 0. So there's no further acceleration going on. It's actually just dropping because we run it to a certain speed and then it halts, drops straight back down. So what happens if we introduce gravity into this? Now, if I uncomment that and then we comment that out, and then let's run that again. Let's take a look at what happens when we add gravity into it. So gravity, as you can see here, we've still got the same input. We've still got that same increase. The effect of this, of the acceleration here, doesn't really change. So gravity has very little effect on what we're actually trying to do. The interesting thing with this though is that we're now in a position where we can change things. We can look at what happens in different aspects. If you want to run both of them in a separate state, we can do that. What I would recommend is that you have the wheel assembly in one state and you have another wheel assembly and just feed the signal next to each other. You're able to do that, which is really good for this type of stuff. Right, now what else did I want to actually add out of this? So we can look at all different types of things that's coming out of it. So I can study the effects of the body itself, what's happening. So I don't want to overcomplicate things with this though. So let's just check on the notes on what type of manual calculation output were we looking for. Based on our note sets, based on what I'm getting here, $185 and 191.1, 600. Actually slightly lower looking at this. Let's just take a look in the states without gravity. As in effect, yeah, it shouldn't really change that, but we are actually slightly lower than suggested, which is interesting with that effect. I'm not sure where there's an inconsistency there. I'm gonna double check that because that has just caught me out as that. So if we need to know the RPM of this, which we very well may need to know the RPM, we all sometimes will need to know the RPM. Now if you look on here, I was looking at the RPM that was coming out. So from here we can do the same. If we go to the positional state of this, So if we go to the position, I'm going to sense that position, I'm going to apply, and then from my position, excuse me, let's have a look on my position. I should be able to, oh, in fact I've got angular acceleration, that should actually give it me already. Trying to think about anything else that I'm missing. No, I've already got them on there. What am I talking about? Right, so I've already got that on there. I don't need to do that. I'm just plucking out random things there. So that is a basic sim for setting up the wheels, looking at torque, looking at what's occurrence with it. Now we've got a particular outputs that are coming from it. We can verify against it. If we need to add more things to it, if we need to add inertia to it, if we need to add custom elements to it, we can easily do that as well. We can do all sorts as far as these systems go. We can add further things to it. We could take this off and we could add a real drastic effect to it. If we wanted to look at what would happen if this started to become affected by the lubrication regime, we could go to inertial mechanics. We've still got that spring stiffness and damping coefficient. If I say on the damping coefficient that this has got a damping that's occurring around it of 0.0001, which ironically can give me some type of output for that lubrication relationship if I run it again, what we actually end up with is a more skewed response, because the second the acceleration drops off, what it does is it says can't maintain it anymore, and actually drops off, and almost in this case responds by it returning on itself, because there's so much restriction in its motion. I can do all sorts with this, so I can implement that even more. Obviously if I make that bigger, it just cannot move. Now some students last year literally said to me, well that's great, but what's the point of being able to do that? So if we're looking at an electric motor, if we're looking at an output from an electric motor, if we're looking at any type of robotic system or turbine system, electric car, whatever, if that joint becomes, if it's defunct and fails, what you can actually do is try and incorporate that idea so you can figure out how much of a failure it would be on that system. Now I use this system a lot for doing motor selection. I've done it for all the different projects that I've done. I've always used this system because it will tell me if a motor is going to do its job correctly, and if I miss anything, because a lot of the time we can miss things, and it's easy to miss things, but we can judge the effects of things by throwing whatever we want to throw at it. Again, this is just a basic wheel, and I understand that this is just a basic wheel, but to solve that problem, to solve and get a result from it, is quite good. So now, as I said, we're in a position where we can change gravity. We can look at what happens with this on Mars. We can really affect this. Now, from these values that are coming out, by converting it from the power string to Simulink, what we're then able to do is extract it and put it onto, we can figure out from Reynolds' equation how much material, not Reynolds, Archer's law, how much material is being broken down and withered away from the actual dynamic system. There is all sorts we can do with it. It is crazy what this thing can do, and it is incredibly powerful for that. Right, I'm aware of the time, so I don't want to rabbit on too much more. I'm going to stop this recording because that is our first session on using the system and getting to grips with the system. I know it's a little bit tricky. For those of you who have found it dead straightforward, you know, well done. Keep going with this. I am going to be releasing more and more and more notes, more tutorial examples that aren't in the notes, but just give you that extra bit of experience. I've put as much reading on the reading list for this module. You should find links to different areas for reading. Just take a look. It's a tricky one to get into, but once you get into it, it is incredibly good for what it's for.